So this week we're going to talk about two important modules in the GA code suite, and especially TGLF and TGYRO.
Correct.
And Brian has kindly offered to tell us all he knows about them.
It won't be all I know. Since this is not a physics lecture, it's a tutorial on using tools to answer scientific questions. We'll provide the minimum amount of background and understanding to be able to understand what is happening without going into gory details of how models are derived or the complexities of these models. I see people are still coming in, so. All right, so I want to start with what are we actually going to try to accomplish today. We're going to show how one can use a modern transport model to investigate the type of turbulence that may exist in D3D reference shot. It's an H-mode plasma condition that we run every morning. And we use this commonly for tutorials because it's a representative D3D H-mode. So for the experts, it's a type 1, relatively low power LME mode with a low frequency type 1 ounce. This is a discharge that was investigated and published in a paper about orchestrating TRANSP simulations. And this was described 2 tutorials ago. So if you go back and look at the TRANSP tutorial, we showed how we looked at the time history of the shot, set up a run to do a power balance calculation, and then looked at the output. So just to remind people, the discharge looks like the following. This is a figure 5 from a recent Fusion Science Technology article, where the plasma has an L mode phase, the power is increased, and the plasma goes into H mode, and it has a long LME H mode phase before subsequent power increases. And we're going to be investigating this discharge around the time of 3.5 seconds. So looking around this time period when the power is constant and the plasma is what I would call quasi-stationary. There's some very long time evolution of, say, the plasma density, but that's okay. It's relatively stationary for our purposes. So just to give a high level of what we're going to be investigating is we're going to be running a turbulent transport model. And I've grabbed this slide from a recent APS talk by Chris Holland, who's a collaborator here at General Atomics on D3D. He's at UCSD. And this kind of captures what a stiff turbulent transport is in the tokamak. And the slide he produced says that hypersensitivity to driving gradients is a defining feature of plasma turbulence. And we're going to use a turbulent transport model in this example. The model is called TGLF. It was developed here at General Atomics by Gary Stabler and others. The main defining feature here is that above a certain gradient, so a profile gradient, that the transport flux here takes off very, very rapidly. And the slope of this curve is related to what we call transport stiffness. So this is what's described here. In practical terms, what does that really mean? If you look at the second plot on the bottom, is that as you put more heating, that the pressure does not rise as rapidly as the heating. So it means that you have a degradation of plasma confinement. And we're going to go through an example using TGLF to make a figure like this top one using real data. And then we're going to try to predict a plasma profile. So here we go. We're going to use a couple of modules here in OMFIT. The first one is called, the module is called Profiles Gen. And Profiles Gen is a translator. There are many translators in plasma physics that translate from one file format or input format to another file format. The example that we have here is going to translate from a transp run into the format read by the GA code tools here. TGLF, gyro, neo, TGYRO. That's the first thing we're going to do. So I'll walk you through that. And then we're going to use those profiles in the transport model TGLF and perform a couple of scans around the experimental values to look at the flux gradient relationship for the condition of interest. And then we're going to go one step further than that. We're going to use that transport model in a transport solver to predict the profiles using that transport model. And so I'll go through all these in detail. So the modules are profiles gen, TGLF scan module, and then TGYRO for the codes. So here we go. The first thing you do, as you've seen in many OMFIT tutorials, this is probably not the first one you've seen, is you go to File and you need to import a module. And the module you will import is profiles gen, which is here. And so you just click load. And I've already done that. So you come here and you say, I'm going to double click on the module. And it's going to ask me, how do I want to start my physics investigation? It defaults to input profiles file, which either you already have or someone gave to you. But for this example, we need to use a plasma state file and a G file. So we're going to select that. And you can select one if you already have one. But for this example, I'm going to extract it from transp using this utility called TRXPL, which is a utility that's provided here at General Atomics. And so it has a number of defaults here. It's going to say get the data from Atlas, which is the local server. The tree is called trans, the token makes D3D. The shot number is 163303. The time is 3500 milliseconds, or 3.5 seconds. And I'm going to use run A36, which I think is the one that I had decided on. And since it's a long stationary plasma, I'm going to average this over about 250 milliseconds. So I'm going to then extract this from the archives. And so I click this button.
So TRXPL is actually a tool that is part of
hold
the...
on, I typed in the wrong thing.
It's a tool that is part of the...
34, sorry.
The transp...
Transp
installation.
Yes, yeah. So the transp installation here at GA or at Princeton or at MIT has this utility. I typed in the wrong one. It's actually A34. Should work. So as another comment is that some of the codes that we used can take a long time to run. And so for this example, I've already pre-cooked all the results I'm going to show. In the event that something happens, we lose an internet connection or something, I'll be able to pull up the plots over here. So typically I'm going to be showing you what I am doing over here on the right. And as we're waiting for some of the calculations to happen on the right, I'm going to show you the result of the calculation on the left, just because we're recording this and you can scrub forward and back in time very easily. All right, so this code has completed. It's extracted my transp run, and it's put it in a format then that's called a plasma state file. And so down here, it'll say the state file is satisfied and the G file is satisfied. So those files end up down here under profiles gen TRXPL output. So the output here is a plasma state file. It's a large netcdf file that contains a lot of information about the state of the plasma at this time. But you don't need to know those details. We've conveniently provided this graphical interface. So the next thing you have to do is you're going to convert the state file and the G file into an input file for the GA code tools. It's called input.profiles. So now you're going to run this code profiles gen. So this is running a command line utility that's installed here at General Atomics or at other institutions. And so after profiles gen runs and does this file conversion, it's got a list of ions that are here. And this will become evident in the future, but what you normally want to do is you want to reorder the ions based on their charge density. So for this example, I'm going to have deuterium, carbon, deuterium fast, and then any other additional species that were in the transrun. Typically, there's a small amount of nitrogen or hydrogen for NSTX is a typical atmospheric gas that is in the transrun. All right, so what happens now? In profiles gen has an output, and that output is a ASCII text file, but is browsable in OMFIT in the tree. It's called input.profiles. And so input.profiles has all of the geometry information and the species information, which ions are there, as well as the power, particle, and momentum fluxes from the transport. This is just translated from TRANSP to GA code.
Particle and energy and momentum sources.
So yeah, the sources, right? So we can plot some of these things. So one of the examples is, the coordinate is called rho, which is the x-coordinate here. But OMFIT has this convenient way of setting rho, for example, as the x-axis. And I can come down here and double-click, and maybe I want to plot my electron density over, the total pressure, for example. And you can see here, this is the total pressure plotted as a function of rho. This is an H1 plasma that has a pedestal here. Okay, so that's an example of running this code to give you the output files, which are ASCII files, that then go into many other codes. And so the next code we're going to look at is a code called TGLF. And so I'll just return briefly to the slide here, that TGLF is what we call a quasi-linear transport model. And this transport model will take the geometry information of the tokamak, the magnetic equilibrium, the Q profile, the elongation, as well as the local gradients that are, from your profile analysis, from your profile fitting. And it'll calculate the particle and energy and momentum fluxes, given those gradients. Now, the whole paradigm of turbulent transport and stiff transport is that you may measure a profile, and that profile has a gradient, but you have uncertainty in the value of that gradient, because a derivative of an experimental measurement typically has at least 15 to 20% uncertainty in it. And so what we do is we explore the space of the gradient and the flux to see how close we are in proximity to a stiff region, or a region where the gradient will take off, a region where the flux will take off for a small change in the gradient. This is a concept that typically has to be reiterated multiple times as people understand the implications of this. It is an important part of transport modeling. So now we're gonna do what I just said, is we want to explore the flux gradient relationship for this case of interest. So I'm going to import a separate physics module, and it's called TGLF, and it's going to be TGLF scan. TGLF scan is a way of running TGLF many times as you scan one of the input parameters. In some previous OMFIT tutorials, it was shown how nice it is to have a fundamental module that's really compartmentalized to do a single calculation, and then you can loop over many different inputs and drive it to explore the space. This is all the concept of a module and a submodule, a driver module and a physics module. So I'm going to load this module. It's called TGLF scan. And the first thing TGLF scan is going to do is going to ask me for my profiles. Since I already typed all that information in, I'm just going to.
You can, if you from the GUI, you can do it. You don't have to do that.
Actually, it won't right now because it won't copy the extra. So,
okay.
All right. So I just copied this profiles gen module deep into this profiles gen module here, just so that way you don't watch me type in all that stuff again. It'd be faster. But this should be familiar, which is the input profiles module that I had just shown before. It has all the same information. And so that's what's then a submodule of the TGLF module. So now you have to set up your TGLF input files. And there's a lot of different options. TGLF is a full-featured quasi-linear transport model. It has electrostatic and electromagnetic, non-adiabatic electrons, various other switches. These are the numerical switches that you don't normally need to set. They're all set to default to be a typical experimental investigation, which is the way we have it set up. So that way you don't have to go through and change anything. So the first thing you have to do is you have to set up the inputs to TGLF. One of the things that OMFIT is great at is because there's so many different file formats, it's it's really powerful for converting one file format to another file format. When we set up the TGLF inputs, it actually drives submodules that produce 100 TGLF input files all across the radius, and it allows us to do scans very easily. So here I'm going to click this button that says set up TGLF inputs, and this will take a second. This doesn't take that long. So to recap, the first thing we're doing here is we're just doing a lot of file translations. And we take it from trans to TRXPL through profiles gen to input profiles. Now from input profiles to, it's called input.tglf. But if you count the number of text entries and button clicks, it really was quite minimal at this point. So it's very convenient. Okay, so now that's done. So we've now mapped all the plasma profiles and quantities to the input file that's required for the TGLF code. So now if you just want to see what we accomplished under TGLF scan, we've produced this OMFIT tree here that's called input.tglf. And at every radius, there's an input file. It's called out.tglf.localdom, which is essentially an ASCII text file. And you can view it if you hit the space bar. You can see all the different input settings. This is exactly why you don't want to have to write this yourself. You can see how many entries are there. You can also view it here in the tree. Because doing that is quite tedious and quite error prone. So the first thing we want to do is we want to say, well, TGLF is a quasi-linear transport model. It calculates a linear eigenmode spectrum for the ion and electron, a linear eigenmode spectrum for the electrostatic potential fluctuations. And then it's going to calculate transport based on that linear spectrum. So we can look at, with our experimental profiles, what modes does TGLF say is unstable? So for this example, we're going to look at a couple of radii, and you just type them in as a list. I'm interested just in the plasma core from row of 0.3 to 0.8, for example. It's a standard region, ignoring the sawtooth radius, and inside the top of the pedestal, where a lot of core turbulent transport modeling is done. So the first thing I'm going to do is run TGLF at experimental values exactly as it says in the button. There's only 6 radii, but what OMFIT does is in parallel, it will log in to a worker node on this computational workstation, and it will run TGLF 5 times in parallel. And so all these little blue boxes are going to turn green as each simulation is completing. Okay. And so this will just take a second. Now you'll see that this doesn't in fact take too long. There's 1, 2, 3, 4, 5, they're done. You see they all finish in approximately the same time. So what we just did is we just mapped in experimental conditions through a turbulent transport model and asked it to calculate the growth rates and frequencies in the turbulent transport at multiple radii, at 6 radii here. And you saw how long it took. It took, I don't know, 15 seconds.
Actually, it takes longer the number of ions you have.
That's true. Right. So if you have more ions, but it took 15 seconds with 2 CPUs. Oh, sorry, 38 seconds. So there was time dilation that occurred. Right? We're doing speed of light or something. It's important to recognize the power of a reduced turbulent transport model. If we were to do this with a gyrokinetic code, that could take hours on hundreds of CPUs to do each one of those calculations. At a future tutorial, we'll talk about how to run a code like gyro. But even to do that linearly, is going to take an hour or two. And to do it nonlinear, it could take many, many hours on hundreds of cores for each radius. All right, so now the most important thing that I want to show is I want to plot the growth rate and the frequency versus the wave number and radius. This is the most interesting plot. All right, so what do we see here? The x-axis is the radial coordinate rho, by the Greek letter rho. The y-axis is k theta rho s, is the binormal wave number. So below 1 is generally the ion scales, and between 1 up to the top here is generally the region that's dominated by the electron scales. And so when I look at this plot, first of all, you have the most unstable mode and the first subdominant mode. TGLF always calculates 2 modes to make the flux relatively smooth. And so what you see here is these are all, in blue is all negative. And
frequency.
Yeah, in blue is the negative frequency, which is in the ion direction, in the sign convention we have here. And red is in the electron direction, and this is a log scale. So up here, all this red stuff, that's all ETG, electron temperature gradient driven transport. And these are probably most likely ITG modes, ion temperature gradient driven modes, which makes sense for this plasma, which is a neutral beam heated, ion heated tokamak plasma. All right, so that's the first thing you want to do. This is just a snapshot of your starting point for doing any physics investigation. I'll close that. So now what we want to do is we want to move on. Rather than looking at a radial map in space and wave number, we want to look at what is the variation of the flux with the gradient. So I'll go back. I want to make this plot. I want to make this plot, and I want to make it for TGLF as my turbulent transport model. So let's go ahead and do that. You have to select the radius because this is a 1D scan. So of course, if you scan any one thing, you have to specify a radius or a wave number, or something has to be held fixed. And so for this example, I'm going to look at the radius of rho 0.7, which is a region that looked like it had ITG modes. It had a negative growth rate, a negative frequency at the experimental values, and it had ETG modes in the high K. And so I'm going to scan something, and the first option here is to scan the electron temperature scaling. And you can scale it by a multiplicative factor, and the defaults are from 0 to twice whatever the experiment is. And I'm going to do it and run it 15 times. And so you just click this button here that says run the TGLF scan.
Can it truly do 0?
Yes.
There's no singularity.
No. No. There's other background profiles, right? So if you scan ion temperature gradient way down, it'll probably find an electron mode. That's because the electron temperature gradient is fixed, the electron density gradient is fixed. So those are all things that provide pressure to drive instabilities. Yeah. So it can do 0 gradients. I don't know what would happen if you gave it all 0 gradients. It might just calculate 0.
Probably will return 0. There's no drive for the instability.
Yeah. Yeah, I can imagine. So this will then take a second, and you see all these things are running. The console over here on the right will just tell you the progress as it goes along and along and along. And so now it's done. And we can make a couple of plots. I just modified a couple of clicks here just to make it more instructive. So we're going to plot the fluxes here. They're actually going to be in MKS units, but it looks the same anyway. I'm going to show all the different individual ions so that you can see quasi-neutrality for the particle flux, and I'm going to use the specific sign convention here. So I'm going to make this plot, and this plot's TGLF scan. So here's what we see. Actually, let me change my figure to make it look a little more bold. There we go. TGLF outputs primarily 3 different transport fluxes. That's the particle flux, the energy flux, and the momentum flux. And here I'm scanning, it says here at the top, RLTS1 is the nameless variable for A over LTE, the electron temperature gradient normalized scaling. And so what you see here is that the particle flux here is becoming increasingly negative as A over LTE goes up. The energy flux goes screaming off to a very, very high value. And the momentum flux is also increased here. Now the stars indicate the experimental value of the transport flux. So as you vary one of these parameters, you want to see the curve moving somewhere so that it can intersect, right? So here, I'll just look at the energy flux first. This is x-axis is A over LTE. The output here, this is the electron energy flux. The ion energy fluxes here are very, very small. It looks like ITG is stable actually at this radius. And the blue curve, the blue star here, is the value from power balance. So what this tells me is that in order for TGLF to be correct and match the experiment, I need to increase my electron temperature gradient from a value of around 0.27 to a value around 3, which isn't too far off. Now the particle flux, you see that it's increasingly negative, that just changing the electron temperature gradient cannot make you match the particle flux. Now as a slight aside, one can always look at the flux spectrum, and I'm just going to give an example here. And you see what happens is that as A over LTE goes up, you're actually you're moving more towards this direction. Okay, so a lot of these modes are becoming more electrons, so going from blue to red. And so those modes are not contributing to the particle flux. So now I want to scan the ion temperature gradient. So the reason why I'm doing these two gradients is because next we're going to use TGYRO, and TGYRO is a transport solver. It will adjust the temperature gradients to try to match those stars. So now I'm going to run TGLF to scan the ion temperature gradient scaling. And you'll see that there's going to be a different character. As you scan A over LTE, you see a very large drive of electron thermal transport. You saw that it shoots off extremely rapidly. It looks very similar to the plot that I showed from Chris Holland's view graph. And now we're going to scan A over LTI. It should be noted that this tool also allows you to do 2D scans. It's going to take a lot longer. Rather than doing 15 here, you're going to do 15 squared. So the capability is completely there for doing these investigations. But this is just one example. This is probably the simplest example. You'll even see examples of this being done in modern publications. People are looking for proximity to critical gradients. So now here I'm going to plot TGLF scan here. So this time I scanned A over LTI. So I scanned the ion temperature gradient. And so now you see something different, which is that now the particle flux becomes increasingly positive. So it actually changed sign. So ion modes and electron modes, as you vary them, it can cause the density profile to either peak or flatten by driving more or less particle transport. You can drive a particle pinch. For the energy flux here, you see something interesting, which is if I look at the ion energy flux, which is in green, the deuterium ion energy flux, you see that there's a very clear critical gradient. This green curve is almost vertical. Okay, so as soon as you pass this threshold for A over LTI being close to 1.7, all of a sudden the flux takes off immensely quickly. So if you go back to the plot that I showed from Chris Holland, once you've heated the plasma such that the temperature gradient is hit 1.7, 1.8 over LTI, you can pour heat into it, and the temperature gradient is not going to go anywhere. Mm-hmm. That's what people refer to as profile resilience, or sometimes it's called stiff transport. What's interesting, though, is that also the ITG mode, which is driven here, is also affecting the electron thermal transport. Here you see a U-shaped curve. Whereas you reduce the ion temperature gradient, it actually makes the electron modes and the electron transport even stronger. But above the critical gradient, now you're driving ion and electron transport. That's a hallmark of an ITG mode, is that it produces similar ion and electron transport. It's kind of this universal instability. So that's one example. And if you really want to get familiar with your plasma of interest, you might do this scan at multiple different radii, grab all the figures, and then move on to say, okay, this is the linear stability, this is the flux gradient relationship. Now I can move on, and I'm informed enough to do profile predictions. Okay, so this is getting you all the background. So let's move on to do that. So now we're going to use a code called TGYRO, which the name TGYRO is confusing to some people because there's a number of codes here. One of them is called gyro, which is a nonlinear turbulent transport simulation. Then there's TGYRO, which is a transport solver. It's not a physics model at all. It's actually a Newton solver fundamentally. And then there's CGYRO, which is the new optimized for high collisionality code that is like gyro. TGYRO, CGYRO, and gyro are quite different. So you just have to get over that. All right. So now I'm going to import that module. And this module is called TGYRO, or TGYRO GA code. And just for the sake of time, I'm going to skip the part where I go through the profile analysis. Just so you know. In principle, one normally types in the information about the shot, but I want to skip over that. I'm just going to get out of that part. So assuming you've typed in the shot number and the time and extracted the plasma state and all that stuff, you'll be presented with this graphical interface, which is the TGYRO GUI. And it has a number of tabs here, the input profiles, which we've already done. There's the geometry, which says how many radii am I going to use. This is really how many different radii am I going to use to represent my plasma profile. At each one of those radii, TGLF and NEO have to be run many, many, many times. So each one of these is like a flux tube. You don't need to make them too closely spaced together. They shouldn't be any closer together than a few turbulent correlation lengths. There's the evolution control in terms of how many different quantities are you going to evolve. You can simulate the electron temperature, ion temperature, density, plasma rotation. These can all be simulated individually or together, depending on how you check them. And so I'm going to start with a simple case. This is the way I usually run it. I'm going to get familiar with my simulation and do this piecewise. If you do it all at once, you may have an answer, but you might not be totally informed as to why you got that answer. So I think it's important to do them in steps. And the first thing I'm going to do, the solver control, which is how many iterations and what iteration scheme you're going to use. I'm going to change a couple of these things based on what I had defined for this tutorial example. And end up being very aggressive here. So the solver control here is how many iterations do you want to run? How do you want to define the residual in the least squares minimization? There's something really convenient here, which is you can set a tolerance that if the solver progresses to a certain state, they'll stop rather than running per prescribed number of iterations. There's the step size in the Jacobian and the maximum step size. What this means, as a little aside here, remember this flux gradient relationship, where this is the transport flux and this is the gradient. TGYRO is going to adjust the gradient to try to get it so that this curve is at the same level of the star in the previous plot. Mm-hmm. And you have to tell it how big of a step it can make in the gradient. And so that's what's called the Jacobian step size. If people know about numerical methods, you form a Jacobian and you try to minimize in a Newton solver. That's beyond the scope of this tutorial, but it's background for numerical methods. There's a number of options for scanning. For example, you can turn the E cross B shear off, which turns out to be important. There's options for using TGLF and NEO, and how many ions do you want to use, and et cetera, et cetera. You should usually just go with the defaults. It's pretty standard. And then any specific TGLF settings, we're not going to change them. I just want to make sure I have this set up right. One of the things, that's really nice is that you're going to end up running multiple simulations, turning various switches off. You want to be able to overplot them, maybe able to compare them. The first thing I'm going to do is I'm going to do what we call an evaluation. I just want to run the model and overplot my trans power balance to what TGLF says the flux is. So I'm going to call that eval. And I'm going to run it at a number of radii here from, I had some notes here, so 7 and 0.2 to point, that's probably enough. So essentially what I'm going to do is I'm going to take TGYRO and I'm going to run TGLF at 7 different radii between row of 0.2 and row of 0.8. It's going to calculate the transport, and I'm going to overlay that with what transp says that the flux was. So I'm going to do it. And as with all OMFIT scripts, it's going to log in to a worker node. It actually submits this as a batch job because it requires, it'll show over here 14 MPI tasks because you have 7 radii and you have 2 CPUs per TGLF radius. So now it's done. That was very fast because I'm just calculating the flux. I'm not solving a nonlinear problem. So I'm gonna, first thing to do is you can just plot the profiles and scale lengths that went into TGYRO. So that's this. Here's my electron temperature that went in. Each one of these circles is a radius where a simulation will be run. And so at each one of these radii, we're gonna run TGLF and TGYRO. We're gonna run them many, many times. This is A over LTE, the normalized inverse scale length that will be used. And here's the one for the ion temperature. See, the ion temperature has more curvature to it rather than being almost a straight line. So you see here that, oh yeah, these are the profiles. And these are the profiles the way that TGYRO will interpret them.
You know why TGYRO doesn't match the experimental lengths?
Well, it depends on how you want to run it. So there's two ways. There's 2 ways of doing this. Okay. So this is so one of the options is you can use the exact profiles rather than integrated scale length match profiles. So the question is, do you want to start with the exact temperature profile, or do you want to cut it to start with the scale length that matched the exact temperature profile? So I'm gonna run this again just to show you the difference. So you saw that in order to match TI perfectly everywhere, that A over LTI was off by just a smidge at one of the edges, right? So now I'm gonna rerun this, but rather than using the measured temperature, I'm gonna use the measured scale length as the starting point. It's all just about the starting point. Because you're using 6 or 8 or even 3 points to represent a profile, you have the choice of the granularity there. As you go more coarse, you'll get more and more of a mismatch. But you'll see in a second that I'm going to use actually 3 points when I do my solve. So let me go back and plot the profiles again. So now you'll see here that the scale length is exactly matched, right? But if you zoom in really close, you'll see that TI is not perfectly matched. Whoop.
So,
but it's arbitrarily close, I would say. Comment?
Yeah, no, TGYRO represents these profiles. Actually, what TGYRO does is it knows about the scaling of the profiles at the points that we prescribe. And then to generate the profiles, it integrates that scaling. So if you want, the profile itself is almost a post-process, if you want, of what the scaling is. So TGYRO itself cannot represent, given a set of points, it cannot represent all the profiles.
Yes, it can't represent both the scale length and the profile simultaneously unless it has the same number of points as the original profile.
Correct.
So one could solve the transport equations at 100 radial points. In fact, transp does that because transp is also involving the current and the sources, and it has one grid. And so what I'm going to show you for one time, transp has to do for 1,000 times. It's a hard problem. Okay, so now what else do we want to plot? We want to plot the flux matching. TGYRO works in gyro boom normalized units. It's not always the best way to make the plot, but I'll show you in both. So I haven't run any iterations. I haven't solved any equations, but it allows me to plot what my power balance transport is, which is the gray curve with the points, and then the output of TGLF and NEO, which is here represented by the colored lines. So looking back, we did a scan at row of 0.8, right? And we found, sorry, 0.7. We did a scan at row of 0.7. And we found that TGLF did not predict a lot of electron thermal transport. We had to increase the gradient in order for the transport to match power balance. So if I look here at row of 0.7, that is indeed true. That TGLF predicts this level of thermal transport. It needs to increase the transport by a lot, okay, by like a factor of 3. But because transport is stiff, to increase the flux by a factor of 3 may take a 10% change in the gradient, right? People, if you're going to be using this tool, that needs to be very internalized, you know, understand that part, right? That's the beauty of the quasi-linear model. It says I only need to predict the linear threshold, okay? Because the linear threshold is close enough to an arbitrary flux.
Yeah, the linear threshold is where the transport
takes off. So I'm gonna remake this plot, but I'm gonna plot it in MKS units just to show you something here. Okay, so this is now in MKS units. Now you can see the whole radius. It's because the gyro boom normalization causes the flux to increase rapidly with radius, right? So here you see that the flux from transmit all these different points is the smooth curve. The flux from TGLF is this ratty, spiky thing. And then over here on the right is the ions. So on the left is the electrons, on the right is the ions. You can just look at the top curve. And so at row of 0.5, perhaps, there's a large instability, a large ITG mode. It's well above threshold. And at row of 0.7, it's slightly below threshold. This is kind of typical. But for the ions, you'll see that the neoclassical transport is not negligible. The green curve here is the deuterium neoclassical transport. And you see that as you get towards the plasma core, as the neoclassical transport goes up and the power balance flux goes down, you get to the core of the plasma and you would see that, you know, perhaps it's at the neoclassical level. It's kind of typical of relatively high confinement D3D plasmas. Okay, there's the same thing here for particles and momentum, and then all the power flows. So you can see here the individual contributions to the power flows. So the total electron power flow, and there's auxiliary heating and collisional exchange. Okay, so now the hard part. We're going to ask the TGYRO solver to adjust all the gradients of the temperature to match that target, to find the root of the transport equations. So simultaneously, it's going to start adjusting the gradient scale lengths all over the place. And it's going to adjust them and find when the model flux matches the power balance flux. And so the solution of stiff transport equations is a generally challenging numerical problem. I've selected a case here that will be relatively fast and relatively simple, but this can cause major headaches for people that try to do transport modeling. You need well-behaved transport models. So for this example, I'm going to change my simulation identifier here. I'm going to simulate TE. I'm going to ask TGLF to predict my electron temperature profile. And the thing I'm going to change is this. Just for simplicity, I'm going to do it on a very coarse grid. I'm going to run the simulation from 3 to 7. So I only have 3 simulations, 3 flux tubes, 3, 5, and 7, 3 different radii.
You have to change the number of equations.
I will, yeah. So first of all, you select your geometry, which is, you have to choose what spatial resolution you want. You have to select your evolution control. Here I'm going to evolve TE. And then you have to say, how are you going to set up the solver? And for this example, I'm going to give it 10 iterations using this iteration method and this residual. I'm going to say if it hits 10 to the minus 3, that I'm going to say is good enough. And you'll see what that looks like. Normally, you can see here it starts off with a residual of like 1.3. So 10 to the minus 3 orders of magnitude. It has to get close.
So the residual is the difference between the star.
Yeah, the difference between the star and what transset and what TGLF says. The star, the difference between the power balance flux and the model-based flux. And I'm going to take some large steps here with the Jacobian. I'm going to be aggressive here. Usually I try to start off being aggressive. Try to make a lot of headroom on the problem, and then you can make it smaller if you have a hard time conversion. So I'm going to submit my TGYRO simulation. Once again, I'm trying to predict the electron temperature profile. I'm using only 3 radii, row of 0.3, 5, and 7, as representative flux tubes that describe the full plasma torus. And so this will take a second. Usually now you can go get a coffee, do whatever you want to do, and wait for it to finish. But like I said, this is like cooking shows. You put the turkey in the oven. You can come over here, and I've gone through all these steps, and now I'm going to show you the result. So here I'm going to load my electron temperature profile simulation as that's running in the background. You would see that I had all these things set up the exact same way. And I'm going to make the same plot that I made before. Usually the first plot you want to make is what is the convergence. You want to see that the transport solver actually worked. If it didn't converge, you don't have an answer. I've spoken to people have stopped into my office and said, here's my profile prediction. I say, did it converge? Okay, because it will just stop. It'll stop after 10 steps. And 10 steps doesn't mean it's done. 10 steps means it went 10 steps. You need to look at it. And so here you see this is the residual. This is the flux matching. And you see this is a log plot. And it reached 10 to the minus 3 after 6 iterations. So it normally is not that nice. But I picked this as a nice example. Okay, so actually the one that I did simulate over here is done. So you saw how long that took. It took 101 seconds. Yeah, which isn't that bad. Okay, so I'm going to plot the flux matching, which is what I showed before. And this is essentially what you want to see. On the left-hand side is the electron energy flux. This is where you started, right? It's like 0, way too big, might as well be 0. And then when it finished, it's here, right? You can't see the difference between the lines, which means that it matched the flux by adjusting the gradients. And so what does the profile look like? You plot the profile and the scale length. Here's the result. And this is very intuitive. You can understand exactly what happened. In gray is my experimental profile, and in black is the prediction after 6 iterations. Like I showed before, you started with no transport at this radius, at row 0.3. So the gradient, of course, had to go up. And at row 0.5, the transport was way too high, so the gradient had to go down. And at row 0.7, it was too low again, so it had to go up. Right? So this is what happened. I just predicted the electron temperature profile, keeping everything else fixed. I didn't adjust the ion temperature. I didn't adjust anything. The only thing that was changed is that as the electron temperature evolves, the power flow through the electron channel depends on TE over TI, or it depends on the TE minus TI. It's called the collisional exchange stream. And so that will then change the target. So even though I described this as a Newton solver trying to hit a fixed target, it's actually hitting a moving target. So the problem's a lot harder than what I had let on. So okay, that's not horrible. This is a very challenging problem, right? You're trying to predict the level and magnitude and the right type of turbulence in order to capture what's happening in the core of a hot D3DH1 plasma. That doesn't look too bad to me.
Brian, can I ask a question?
Yeah.
So in that case, can you come back to the plot?
Sure.
So you had only 3 real locations where you predict the gradient, but the profile looks very smooth. So how is that?
Yeah, so it's integrating the scale lengths across a finer mesh.
Well, it's
Okay, so it's linearly interpolating
so correct. So
Linearly interpolating the
if you look
gradients.
at the bottom left corner, right, TGYRO is interpolating exactly that scaling, and the way TGYRO, we calculate just 3 points. TGYRO knows that the scale length on axis should be 0.
Yeah.
And the integral is done assuming that the scale length varies linearly between the 3 points.
Okay, okay.
That's right. That's
So
right.
you know, when you get when you have a linearly varying scale length, you get something like exponential profiles.
Yeah. It's a exponential of the individual scale. It's an integral over an exponential.
Right.
Yeah, it's pretty straightforward. And what you'll see is that, well, the scale length at this radius changed, the value of the temperature doesn't change. So I'll zoom in here, and you can see here that this thing doesn't. No, it doesn't like me. I need to close this window. Having a technical problem with that plot. I'll plot it again. So what happened is that the gradient didn't, the gradient changed, but the profile value didn't change. So as you come in here, you see exactly what you would expect, which is that my measured profile is this gray thing. In order to match the transport, TGLF says that no, your gradient should be this. Okay, and then they're not too different.
Mm-hmm.
This magnitude of a variation of a gradient caused this, tweak or raise to the profile value. Okay, so then if I come over here, I can do the exact same thing and plot the result. So in interest of time, it's now almost 2 o'clock. This is almost done. I've repeated the same exercise, just going in and switching over here. Evolution, I would just say, turn off TE, turn on TI. And you run the code, and you plot the result. You can plot the flux matching. Here, this one was a little bit of a challenge. It had a challenge here. It didn't quite match. I need to take a smaller step size. You see the neoclassical level is quite substantial, and TGLF is just very, very marginal at this radius. It's a little bit off, but it's close enough for a demonstration. And so then I'll plot the profiles and scale lengths here for this example. Now TE was fixed, and I predicted TI. So that's your result. You see it in gray, once again, is the experiment, and in black is the prediction from TGYRO. You see the gradient also has this seesaw character. It's a little higher, a little lower, a little higher, okay, compared to the measured experimental gradient, which is in gray. The same exercise was repeated for now predicting both TE and TI. So here you plot the temperatures again. And what you see is if you predict both of them together, actually, it comes out being closer to the experiment. TI is similar, but TE now is actually much better. That's because some level of ITG means that A over LTE doesn't have to go so high to cause ETG. Developing some intuition about this requires going deeper than just looking at the profiles. You need to look at what TGLF actually showed. But the practical result is what I'm showing here. And then you can also predict the electron density. So here now I show the profiles and scale lengths. So this shows an interesting feature. So now the temperature comes out slightly higher of the electrons, slightly higher for the ions. And that's because the electron density was predicted to be slightly flatter than what we measured. So as the density goes down, temperature goes up. Now, this is not a case for detailed validation. In reality, you should have at least a couple more points to map out a profile and do some uncertainty quantification, which is something that we'll hear about in a different tutorial. But essentially, this is then a starting point. So now you're able to say, you can look at TGLF and say, well, what about if I include electromagnetic fluctuations? What's the role of E cross B shear in this? You can turn that on, turn it off. You can do many different things here. One thing that we can always do is we can always compare all of our runs. So if you want to make a comparison of all the different simulations here, I can click on this button, and it'll show for every simulation I've done, what's the result. So here I have a number of different profile predictions and profile gradients with various physics assumptions that are defined here, whether I'm predicting electron temperature, ion temperature, both electron and ion temperature, or including a density prediction. And all of these things orient you as a starting point for saying, how could I improve the transport in this regime? Or what happens if I turn on direct electron heating? Or what happens if I go to higher or lower rotation? So that's essentially what we wanted to talk about today in this tutorial, using TGLF and TGYRO to investigate the turbulent transport physics for tokamak discharges and make profile predictions.
Very nice.
Any other questions from offsite?